So my name is Graham Stevens. I'm an application engineer here at KETIV, focused on Ansys products. I have 25 years of product development, consulting, and simulation experience, and I provide application support for Ansys mechanical, high frequency, and low frequency applications, which is the focus of our topic today. For this webinar, I wanted to do a broad brush sweep of all different kinds of strategies you can use to speed up your simulations, both on the mechanical side and on the electronic side. So we'll be covering both as we go through today, sort of switching back and forth. And the focus today is really on these four main strategies for improving your simulation time. The first one is called reducing complexity, or the amount of computation per mesh element. The second is called reducing size, trying to reduce the number of mesh elements that you're analyzing overall. There are some solver type and settings that can help speed up your simulation. So if you use the right solver for the right job, we'll go over some strategies there. And then finally, we'll be looking at computational configuration. We sometimes get questions relative to do I have the right configuration of my computer in terms of memory and cores to take advantage of high performance computing, which is what HPC stands for here. So what hardware and software settings do I need, and how does all that work, and how do I make sure I'm getting the most out of the equipment I have? And so the subtopics relative to reducing complexity, we'll go through simplifying the physics and geometry and reducing nonlinearity. We'll be looking at reducing size by taking advantage of symmetry and dimensionality and mesh type and refinement options. On the solution side, we'll be looking at solution methods and different strategies to speed things up there. And then finally, we'll be looking at our high performance HPC software and hardware settings. So reducing complexity, computation per mesh element. The first thing you want to do in terms of reducing complexity is to understand your objective. So why do we do an analysis in the first place? Why are we doing FEA? And in general, it's to obtain information on which to base a decision. And the information you wish to get should govern all your decisions about the analysis approach. So if there's one area of the design that is important and critical that you're focused on, that's what you want to focus all of your FEA on, and sort of get rid of the rest of the stuff, essentially. And as part of this, you need to remember that each model has a region where it's more accurate, and then there are regions where it's less accurate. And of course, you want the most accuracy in the region of interest in terms of what your objective is. So just try and, when you very first start out for a model, you need to really define your objective really well so that you can use that as a focal point for all your analysis. And then in terms of reducing complexity, it's best to start with a simplified model. And the simplest model ever is basically a block. And so a block, a simple beam, a dipole, a simple trace, something that has the rough edges of what you're trying to do there. Make it very simple so that it will solve really quickly, and then ensure that your analysis setup is correct, that the result graphs are as desired. If you're looking for antenna gain, you've got the right settings there and types of analysis. And then look at the physics and make sure that you can kind of validate those either analytically or with back of envelope checks. And once your simple model is in place, then add complexity, add your complex geometry or your slightly more complex loading conditions, et cetera. And in terms of speeding up analyses and reducing complexity, one of the major focuses is on nonlinear analysis. And there are three main sources of nonlinearities. One of them is geometric nonlinearities. So if a structure experiences large deformations, then it's changing its geometric configuration, and that can cause nonlinear behavior. So if you imagine a fishing pole that's getting pulled, 180 degrees as you're yanking on the fish, that is an example of a geometric nonlinearity where the deformation is just really high in the geometry. Similarly, on the material side, we can have material nonlinearities where you have a nonlinear stress-strain relationship, such as metal plasticity shown here. It could be a BH curve in terms of magnetics. There's a number of, it could be viscoelastic materials or hyperelastic materials that don't exhibit simple linear behavior. And this is most of where nonlinearity crops into designs and working with FEA. And then finally, contacts, where you have changing status of a part that is contacting something or not contacting something. That creates an abrupt change in stiffness that occurs when the bodies come into or out of contact with each other, and that is felt as another nonlinearity in terms of analysis. And the reason we're talking about nonlinearities is that nonlinear analyses take much, much longer to simulate. And the reason is, of course, is that to solve a nonlinear problem, we have to basically linearize it. And when we do that, we do multiple iterations. This is an illustration of a Newton-Raphson iterative analysis for one increment of load, where we have four steps here that are taken just to get one load step. So 4 iterative series of approximations to solve. And because you have these multiple steps going on each time you're trying to solve, it just takes much, much longer to solve nonlinear analyses. And so for that reason, we want to just avoid nonlinear analysis as much as possible. And similarly, we want to use linear dynamic analyses rather than transient if possible. So on the electronic side, most of our nonlinearity comes from materials. So when we start with our analysis, it's best if you can use idealized materials, a perfect conductor or PML surfaces, just to, again, get a sense of the physics in terms of what's happening. Then perhaps shift to a material with simple linear properties, copper, irons, your standard materials that are there. And then finally, when needed, and only when needed, jump to an isotropic or BH curve materials. And of course, the BH curve is important for magnetics in a lot of instances, so you will need to do that. But the idea here is to try and avoid it as much as possible. And similarly, on the mechanical side, it's best to just start with default structural steel, run an analysis there, and then you can also tell if the material properties that you're adding in is what's causing issues or changing your analysis. And then there are a number of switches that I've kind of fingered here in terms of turning nonlinear properties on and off and turning nonlinear analyses on and off that I wanted to just finger for a minute. So on the right side here, if you are using nonlinear properties for your materials, hyperelastic, plasticity, viscoelastic, etc., and there's a whole host of nonlinear properties here. You can see the linear magnetic materials or nonlinear magnetic materials. So when you start using the nonlinear materials, mechanical automatically turns on a nonlinear analysis. And there's a switch in geometry where you're assigning materials under the geometry and then material and definition of nonlinear effects, and you can turn this on and off. So even if you've assigned nonlinear properties to the material, you can say, well, ignore all the nonlinear properties, let's just do a linear analysis by switching this switch here. And so I just wanted you to be aware of that. Similarly, in the analysis solver settings, when you're looking at that fishing pole or geometric nonlinearities, there's another switch called the large deflection solver control underneath your analysis settings. And if that is on, it turns on the nonlinear engine to do calculations. And so again, that switch combined with the material switch tells Ansys, is it nonlinear or is it linear? And then finally, there's a way to check whether you're running a linear analysis or a nonlinear analysis. If you go into your analysis settings and analysis data management close to the bottom, there's a flag here that's grayed out, so it tells you whether it's turned on or not automatically. And this is a place to check: am I running it nonlinear or am I running it linear? Sometimes you might inadvertently include a nonlinear property, and it shows up as nonlinear here. This is a place to check to make sure I'm running a linear analysis first. And then on the contact side, which is a common source of mechanical nonlinearity, as I mentioned before, when the contact switches from in contact to separated, there's a nonlinear jump in properties, and that can lead to non-convergence, and also leads to these multiple iterations and a slower solve. And so there are some strategies to avoid this as well. So one strategy is to consider using joints instead of contacts. There are pros and cons to both, so you have to be aware of that. But you can also use linear contacts. So bonded, no separation, or frictionless contacts are all linear in character, and so they run much more quickly. But if we add in the effects of friction or a rough contact, those are by definition nonlinear contacts, and we should only consider or use those if they're really needed. So sometimes the consideration of friction is needed in your analysis, but a lot of times it's not. And so if you can avoid it, please do, because it'll speed you up. Then we diving a little bit deeper into more of the details here. There are contact formulations in terms of how Ansys handles this situation of the penetration of one surface to the other and its contact. These are called normal Lagrange, augmented Lagrange, pure penalty, and NPC. And just to be aware of your options here, typically the augmented Lagrange is the default. You can sort of see it has a medium computation time. And if you have some contact issues, you might have to switch to normal Lagrange to increase the accuracy, but that'll cost you a little bit more in terms of time. And similarly, if you're looking to speed things up really a lot, you might switch to a pure penalty contact, which has lower computation time, but may lead you to too much penetration or issues there. And then finally, using MPC contacts for shell solid and shell shell and beam shell contacts is a recommended practice as well. And as you're going through your contact formulations and looking at contacts and convergence, sometimes it's useful to change the normal stiffness factor and or the penetration tolerance to aid in convergence. And along those lines, conduct a contact stiffness study if you're running into those sorts of issues. And that's where you simply vary the contact stiffness and see if it changes your both convergence and or your results in terms of accuracy. And then we come to geometry in terms of simplification. So as I mentioned, relative to your objectives, you want to remove things that don't matter relative to your objectives. So if all these gears don't really matter, if the mechanisms here that the fan blade is doing doesn't really matter relative to finding the natural frequency of vibrations that you're doing a modal analysis for, or looking at whether this shroud is going to break under various forces and so forth, then you want to simply eliminate or simplify those geometries. So simplification can take many forms. A lot of times it's removing or polygonizing curves, removing splines, removing rounds, fillets, and chamfers, holes, protrusions, depressions. It's just getting rid of complexity and getting back to that simple block or a simple primitive to reduce the amount of work that's needed to solve the problem. And then relative to edge cleanup, geometry cleanup, you want to try and eliminate gaps, small edges, and sharp angles, which cause the mesher issues in terms of topology and meshing issues. So this geometry simplification is a very useful tool to get you to faster simulations as well as easier to solve ones. Similarly, when we look at aspect ratio, because the ideal mesh element is a block, when we have really thin parts, you can sort of see that these create to keep to a 1-to-1-to-1 ratio in terms of aspect ratio for a good mesh element, that requires a lot of extra elements when we go thin. So when you have part dimensions that are large relative to a thin dimension, then the aspect ratio of the part gets large and your mesh quality goes way down if it keeps to that ratio. And so then you need a huge number of elements. So try and avoid thin parts if you can. And then if you can't, consider using shell or solid shell elements within mechanical instead. And then on the electronic side, of course, look at HFSS 3D layout for your two-dimensional parts. And then within mechanical, there is something called defeaturing, where you have this mesh defeaturing under sizing, under mesh option. It's usually turned on automatically, but you want to be aware of it. And it will essentially go through and eliminate features that are too small to make a difference, or it'll defeature the small stuff essentially automatically. And so you want to be aware of this setting and aware of this global minimum size and what that setting is for your this defeature size setting in terms of well, how big is it, how am I defeaturing or not? But just take advantage of that with regards to reducing complexity as well. And then finally, on the simplifying complexity side, I would just wanted to touch base on coupled physics. So when we have coupled analyses, if it's thermal, electrical, or structural and thermal, structural and electrical, and you're doing coupled analyses where you're pulling together two different kinds of solvers, whether it's Fluent or mechanical or Maxwell Electronics Desktop, you want to first keep it simple, stupid. So is two-way coupling really necessary? Because of course it is more complex and it takes longer to do these analyses. Are the analysis conditions, whether that's temperature, deformation, et cetera, large enough that they will impact the other analysis material properties or input conditions? So is there a feedback loop around that? So if I have a really large temperature regime, I might increase or decrease the conductivity of copper, which then increases or decreases the amount of joule heating that copper experiences, which then impacts temperature. So you have a feedback loop there. But that only is valid if the temperature range is really, extreme relative to how much those properties change over temperature. So you just want to be aware of that and try and eliminate the need for two-way coupling if possible. And then as you're setting these up and doing these, it's useful to run each analysis separately. So run the structural analysis and run the electrical analysis separately. Ensure that you've dialed those in terms of boundary conditions and loading conditions for both analyses separately, so that they're separated. So that then when you combine things in a one-way coupling or two-way coupling, you both have some pre-knowledge of what is expected, and then also have already debugged the single analysis separately. So that is a useful thing as you're doing coupled analyses. So then we're going to jump to the second strategy, which is called reduce size, number of mesh elements. So for this, we want to reduce the total degrees of freedom. And there are a couple of ways to do that. One is with symmetry, take advantage of symmetry. Within Ansys, if you have a plane of symmetry, or if you have cyclic symmetry around 360-degree axis of symmetry, you can model just that section of the cycle, or just that quarter of the model. or half of the model. And when you do that, of course, you throw out the other half, or you throw out the other 3/4, the other 9/10 of the model. And that means a lot less work. And so it takes a slight bit more work to just set these symmetry planes up and define things that way. But it's definitely worth it in terms of the savings and speed that you can get. And then on the dimensionality side, you want to ask yourself, is this an analysis that I can actually do in 2 dimensions rather than 3? So a lot of times with motors, we have axisymmetric parts or axisymmetric geometry. And in that case, we might be able to get away with a 2D analysis of the cross-section rather than needing to do a full 3D analysis. And sometimes there are 3D effects that are important, so you have to balance things. And then in mechanical, can I use a beam element or a shell element or a solid shell element instead of solid elements? And that will reduce the amount of elements, nodes needed to solve and speed up analyses as well on the dimension side. Then in mechanical, you have the option of using hex mesh versus tet mesh. And you can see sort of the bottom right here, the hex mesh here is this large cube, which has many more points for a volume, but it also covers more volume total. And as a result, relative to the total volume covered, one of these hex elements, you could sort of see the relative volume here versus a hex element. The hex element, the tetrahedral element, you would need roughly six of them to fit into this hex mesh element. And as a result, you reduce the amount of mesh required for a certain volume by using hex mesh. But to do that, it usually requires a longer time for setup, for cleaning the geometry, and what's known as geometric decomposition. So the tet mesh, you can see in these top figures here, where you have very complicated mesh areas, the tet mesh can adapt to all these complex surfaces much more easily than the hex mesh can. But if I have a simple shape that's sweepable, as you can see in the bottom, then the hex mesh is sort of the way to go in terms of speeding your model up. And so I can take some of these hex meshable surfaces areas here by chopping things up and then hex meshing each of the individual pieces. But chopping them up and defining that and making sure all that works requires a lot of extra setup and time. And so you have a trade-off here in terms of, do I want the optimum mesh, or and which will take a certain amount of time to set up, or do I just want to do a lot of extra tet meshes or a lot of extra tet elements and just run it really quickly? And so you have to make those trade-offs. But if you're looking to get as fast as possible, hex is sort of where it's at on the mechanical side. And then on the mechanical side, there are these settings called curvature and proximity. Curvature tells the mesher essentially, if I have this curve that's going around 180 degrees here, how finely divided do I want that curve, essentially, in terms of, and it's set based on an angle. So if I set it as 10 degrees, the 180 degrees will do 18 segments. If I set it as 20 degrees, it'll do 9, etc. So it tells you how fine a mesh you want on the curves. And proximity is a setting that tells you how many elements do I want for an individual area. So in this bridge here, in this bridge, we have 3 or 4 elements here, and proximity tells you, well, I want 2 elements between surfaces, or I want 3 elements between surfaces, or 4. And generally, to get good results, we want at least 2, and 3 or 4 is sometimes necessary as well. So this is a way of sort of setting your meshing to get enough mesh in the right spots, essentially. So as I mentioned, there's a big trade-off between the man hours of setup versus auto meshing. Ansys mechanical does have some sweep and multi-zone meshing methods that help in speeding up that hex auto meshing. Just be aware that adaptive sizing only applies for a tet mesh. As I mentioned, for capture curvature and capture proximity, some reasonable starting points are 30 degrees for curvature normal angle and proximity gap factor of 2. And then sometimes it's folks that are used to doing very fine and detailed meshes may want to have conformal mesh using shared topology, but those also have trade-offs, so they can eliminate connections, which speeds things up, but it also can promulgate too fine mesh throughout. As the conformal mesh conforms to those surfaces, you might end up with too fine a mesh. And so again, it's just really important for parametric or nonlinear analyses where you know you're going to run into long run times, that it may be worth it to take those hours of setup time. But in many other cases, it's easier just to add more TEP mesh and just solve it and be done. And then on the mesh quality for your contacts, these are just some settings here. You want to set the mesh quality error limits to aggressive mechanical, which it puts more mesh in the contact areas, essentially. You want to make sure that your areas of interest have a quality of your mesh greater than 0.2, so that your aspect ratio is not too thin, essentially. You want to use mesh contact sizing to ensure you have enough mesh to follow these surfaces well. And then finally, use the contact tool to check contacts prior to solving. So if we check the contact prior to solving, you can sometimes debug things much faster than waiting and letting it solve, and then, oh, there's an error and you've got to go back. So we definitely advocate using the contact tool to pre-check things. Then on the electronic side, we have a couple of mesh types here, tau, phi plus, and classic. And these are sort of the best suited for curvilinear surfaces, two-dimensional layered structures or bond wires for phi plus, and then rectilinear surfaces for classic. Electronic meshing, of course, uses automated adaptive meshing. And so there is a lot less knobs associated with meshing within the electronic suite. And generally, you want to just run it with your automatic mesh and adaptive mesh and be done, and not actually do any changes. So I have this one tip here in terms of your ASYS checks. You can turn those off, which may help you to mesh more items. Just because you fail an ASYS check doesn't mean it will not mesh. And then if, and only if, you feel like, time is a priority and that's something you're exploring reducing, you may want to pre-finger areas. So in this particular area, I have the arrow here where you have a lot of mesh points here, and that a priori, it's a magnetic, the magnetic gradient around there is going to be really high. And so you can finger those surfaces and create denser mesh in that area at the beginning. And by so doing, you can sometimes reduce the number of cycles that the mesher is using to converge and to do its automatic meshing. So it starts with an initial mesh as shown here on the right, and then it looks at, well, where are the gradients, and it adds more mesh in those areas, and then it does it again and does it again. So there are many cycles and loops associated with meshing multiple times, and you can reduce the total number of loops if you say, well, I want more mesh right in here and right in here from the get-go. But of course, when you do that, you might be telling it to put too much mesh in somewhere that's not needed as well. So you can slow things down as well. So you want to be careful with this adding mesh operations, but it is useful and sometimes a good way to speed things up. And as you're doing that, make sure that you do a minimum of 4 passes rather than just meshing a whole lot of mesh and doing it in 2 passes. Kind of negates the whole advantage of your adaptive meshing. And then as we look at mesh density versus accuracy for electronics, your automatic adaptive mesh refinement allows you to set the desired accuracy directly in the solver settings. So you can set your accuracy as 5% or 1% or 0.1%, whatever you're looking for. In mechanical, that is not necessarily the case. If you have a TEP mesh with a mesh convergent object, you can actually set your accuracy that way. But in a lot of cases, we may want to do a mesh refinement study where we're looking for the minimum amount of mesh that will not change results. And so you do an analysis with 30 degrees and 2 on proximity, and then another one at 10 and 4, and see if the results change. And when they don't, you know you've got enough mesh, and you've got a refined enough mesh to get the answers that you're looking for. Some other checks that you can do along those lines in terms of, is the mesh accurate enough for what I'm doing, is look at the average versus unaverage stress and strain. If those are a small difference, then you know you've got good enough mesh. And similarly, stress error versus strain energy. Okay, so jumping into the third strategy, this is solver type and settings. So for HFSS in particular, for the electronic solver, there's a number of different solvers buried within HFSS depending on electrical size. So there's HFSS and finite elements. There's another called method of moments, which looks at the surface the surface electromagnetics of surfaces, and has basically an approximation. So it just considers the surfaces rather than volume analysis. So it's faster, which is applicable in some cases. And then finally, when we get to very large models and we're looking at large objects far away from other things, we can then use asymptotic and shooting bouncing ray analysis. So this looks at battleships and radiation patterns at long distances and within cities, and just very large areas at large electrical sizes. And then finally, if we get to higher material complexity, there's something called HPC with domain backplane, where we basically chop up the analysis so that we can do these larger analyses and solve each of the pieces individually. And we'll get to that a little bit later as well. But I just wanted to be aware of these different solver methods in terms of versus electrical size when you're considering HFSS analyses. And then there are something called a direct solver in both mechanical and electronics, ADT, and an iterative solver. And typically the direct solver works in core. It leads to better performance because it's using basically more memory, and because it uses more memory, it uses less input output to the hard disk, and that saves some time, or saves a fair bit of time. So depending on the complexity of the model, the size of the model, the direct solver can be much faster. For larger models, it tends to be the iterative solver tends to work better in terms of speed. And then similarly on the mechanical side, you want to just use the iterative solver for your linear analysis. But when you've got a nonlinear analysis, the direct solver might be more resource intensive, but faster. It might be faster. The iterative solver may have convergence difficulties. And there's a new feature in mechanical under right before you get to the solve, right next to the solve button, there's a resource prediction button that you can press as well in mechanical and get a sense of is the direct solver or the indirect solver more applicable to this analysis or not. So be aware of that as well. It's a new feature just the last year or two. And then relative to reducing your nonlinear analysis time in mechanical, run a linear analysis first, see if that's good enough in terms of the physics that you're trying to do or what you're trying to do. But if you do need to go to nonlinear, you can start looking at conducting a nonlinear time step study to reduce the total nonlinear iterations. So for this analysis here, you can sort of see kind of from 4 to 10, there wasn't a whole lot of change here. So we probably don't need 10 steps initially to run here. We could probably get away with 5. Well, you may want to test that. And so you would run it with 5 only to ensure that you're still getting convergence. And so optimizing these number of steps can definitely speed things up And so you can also sort of start small and run it at low time and make sure you're getting convergence and look at convergence, and then expand to see if you need to. And then sort of similarly within HFSS, there's something called basis functions, where sort of similar to the hex versus tet mesh choices, there are choices around where the nodal values are assigned. So it's called the zero basis function, the first order basis function, or second order basis function, where you're assigning to vertices edges, and vertices edges faces. And so you have many more unknowns per tetrahedron. The automatic or the default is mixed, where the Ansys HFSS assigns basis function based on the need for higher accuracy in different parts of the model, and that works well most of the time. And sometimes you can get away with first order, and it can be faster than the mix. So this is an option just to think about if you're looking for high runs or looking to reduce computation time. And similarly, whether we're doing frequency sweeps in HFSS or Maxwell, or we're doing a frequency sweep for harmonic response analysis within mechanical, if you can select individual frequencies that are important and reduce the total number of frequencies in the sweep, that can lead to faster run times. And then just be aware too of the differences in HFSS anyway between the discrete sweep, the fast sweep, and the interpolating sweep in terms of how these are calculated. They each have their advantages and disadvantages, and definitely go into ALH and dive into that to make sure you're selecting the appropriate type of sweep for what you're trying to do as well. And I just wanted to reiterate, depending on your objectives, do I need just a really fast analysis that's really quick and dirty? Do I need it to be really accurate in this particular area? Am I planning to run this analysis multiple times over and over again? And so therefore I need to get the best mesh in the tightest time possible. On the mechanical side, you've got that setup time to optimize the mesh issue, and then you've always got sort of accuracy versus total amount of mesh to trade off in both mechanical and electronic in terms of what you're trying to do. And a lot of times it's useful to sort of start with a really coarse mesh, a really coarse analysis, just run it and make sure everything's set up properly, and then refine later to get sort of your final run, so to speak. So then there's another strategy on the solver side that's called reduced order modeling. And in the Ansys universe, reduced order model usually refers to reduced order model at the system level, the right side of this slide, where you create a reduced order model by conducting an FEA analysis on a particular component that may be a fluid problem or an electronic problem. You parameterize the driving variables, you correlate those to the outputs, and then you use some sort of correlation function to represent that whole system in just an equation. And of course, when you do that, it gets very fast. And then that is used for, if I have this particular smaller component that's within another larger assembly. So I'm looking at a car or a battleship or something where you have a lot of different components, a lot of different systems. This sort of analysis can really help to enable you to analyze with fidelity the system as a whole. And when we apply that sort of thinking to a particular finite element analysis model, now say in mechanical, there are within mechanical, you have a number of objects that are modeling stuff, but not directly within the FEA. You're describing the spring and how it operates. You're describing the joint and what its constraints are. And then those few constraint equations the action of the spring is calculated, but you're not actually modeling, the spring deformation as it's going back and forth within FEA. And so that can speed things up a fair bit for a number of these situations where there's point masses or bolt threads, et cetera. So just being aware of and taking advantage of situations where you can model a phenomenon through these additional elements in the model is essentially sort of a reduced order modeling, but in mechanical. And then we can also think about box within box strategies. So in mechanical, there's something called super elements, where you characterize a group of elements by their equivalent stiffness, mass, and damping matrices. So you run an analysis, you characterize it well, and then you create this super element that has far fewer degrees of freedom and replicate and use that super element in large structures or systems. And that can then save a lot of time when you're doing superstructure analysis. Somewhat similarly on the HFSS or the, I believe Maxwell's, well, I can't to double check on Maxwell's having 3D components, but you have the ability here in HFSS at least to do an analysis where you run an analysis just on a small area, you're including your boundary conditions, including your excitations, including geometry, everything. And then that small analysis block gets called a 3D component, which you can then use where you replicate it in another larger array. And that analysis has been pre-done and it feeds up to the system level of the larger array. And by doing so, I can run, 3 different analyses here where the outside corner, the inside corner, another section, and I just run those 3 analyses, and then I can immediately, get to a larger analysis much faster. And so this strategy can help speed things up. And then Mesh Fusion takes that to on steroids essentially, and kind of allows you to mix and match the micro to the macro. So if I have small components inside larger assemblies, it allows those meshes to fuse and be valid and used. So it allows you to solve new kinds of things, and sometimes it's faster and sometimes it's slower. And then on the mechanical side, there's something called submodeling, where you might be interested in deformation of just this particular joint, and you start with a larger area and body of components you're considering, run a very coarse mesh and a coarse solution on that, and then focus in on the area of interest with a second analysis. And you could do it where you take your initial large analysis and just create a lot more mesh points and just solve that. But that can sometimes take a really long time versus solving 2 models where you have a very coarse mesh for one and a very fine mesh, but a much smaller area for the other. And a lot of times by doing this sort of submodeling, you will save time. So I just want you to be aware of this technique. And you want to submodel when you cannot include enough detail or enough mesh to get accurate stresses in a localized region is another use for submodeling. And as you dive into ALH, in other words, you'll discover how this works from a physics perspective. There's a cut boundary displacement method based on St. Venant's principle. So I encourage you to go find out more about that as well. So another strategy to reduce analysis time within HFSS is if you can substitute circuit analysis if you have RLC boundaries. So if I have a capacitor or an inductor that is modeled as an RLC boundary within HFSS, I can, rather than running multiple versions of HFSS with different values of inductors or capacitance or resistors, I can use an analysis where I can change my topology of how I'm doing analysis, where I use a port instead of the RLC boundary, and then I feed that to a circuit analysis, which changes the RLC values, and that can be much, much faster because circuit is much faster than HFSS. So if that's of interest, check out this YouTube webinar, HFSS and Circuit Synergy, using circuit instead of RLC boundaries as a way to speed up that type of analysis. And then finally, within HFSS, of course, HFSS has been focused on antenna arrays, phased antenna arrays, for a long time, with a lot of different ways of slicing the cake and changing your approach. And so this unit cell infinite array to finite array to explicit simulation. And lately there's a new 3D component array that should be added to this pantheon. Just be aware of these different methods and analysis approaches, their advantages and disadvantages in terms of speeding up the simulation and really taking advantage of these new solver settings and methods. So then we finally get to computational configuration, where we're looking at our hardware now to speed things up. So the first thing is thinking about model scaling. So when we think about model scaling, if I have a parametric analysis or an optimization where I'm looking at varying size of a body, 1 to 5, 10 to 20, and I'm trying to optimize for that. And so I'm running my model multiple times. When I'm running my model multiple times, I can send each of those model runs to a different computer or a different processor. And so it scales very effectively. So you get one-to-one scaling. I add a new processor, a new core, and I get, it speeds it up twice as fast. When I have a large or a complex model, it scales sublinearly. So when I have a larger complex model, I'm chopping up the computational job and sharing it between machines. But that process of chopping it up and sharing it with machines results in there's always some lag or some issues both in memory restrictions or in speed of transfer that won't allow it to double your speed by adding a new processor or a new computer, so that it scales sublinearly. You will still get speed ups, but not quite as much as if you're doing parametric or optimization. And so because it's in that, the amount of speed up you get is model dependent and situation dependent, and to some extent settings dependent, which is some of what we're covering today. And so it's useful then to create a benchmark. So look at the typical analyses you're running, the typical types of models you're doing, and send that to the Ansys benchmark program, performance benchmark program, to really get a good sense of, well, if I go up to 10 processors or 10 cores, is that good enough, and that gets me most of my speed up, or do I really want to go to 40 or 100, and really get a sense of what that sublinear curve looks like for your models. And then we'll dig into some hardware configurations and some checks you can do on your computer in terms of making sure you're set to run as fast as possible. So the first option here is looking at your BIOS settings. In particular, we need to disable hyperthreading and then make sure turbo boost mode is active. And usually it's enabled by default, so you won't usually need to finger that. But hyperthreading is usually activated on most machines today. So you have to go into the BIOS to set that up, which is sort of the underlying basic input-output system. It's sort of a core system underneath your Windows or Linux operating system. And so to get to it, you press a key when you first turn on your computer, and then you come up to a BIOS menu that you can kind of sort through and make sure you turn off hyperthreading. Then we talk about memory and making sure that we've got enough memory for the job, that your machine is right-sized for the job. And so for mechanical, you want about 15 gigabytes of RAM per million degrees of freedom. And for Ansys, CFX or Fluent or HFSS and Maxwell, you want about 8 gigabytes of RAM per core. And so you can tell how many cores you have by looking at your Control-Alt-Delete and computer performance. The cores are sort of listed in the bottom right of your Windows machine. And ensure that you have enough memory for the types of analyses you're running. And then once you have enough, you also should check your memory bandwidth balance. So what that means is within your computer, you have a number of memory slots. And if you have all of your memory in one slot or two slots, but none in the others, that's very unbalanced. And what you want is the same amount of memory in all the slots. And so an easy way to check whether your computer is set up this way, set up properly, is to do this command line prompt here, type that into the command line. Sorry, it's so long and complicated. And you'll get an output. And you'll be able to look at all the individual channels, and you want to check and make sure that those channels have identical amounts of memory, essentially, so that you're balanced. And then other hardware configuration concerns. Of course, we want to think about processors in terms of both processor speed, the gigahertz, and the generation of the processor. And essentially what we're finding here is that processors older than about 3 years ago can be much slower. So as new innovations in processors show up, one of the key things they focus on actually is finite element analysis. Can I run my finite analysis faster? And so they optimize for that, and they change the core base of the processor and how the architecture is done for FEA. And as a result, if you're using an older computer, you're probably going a lot slower than you might otherwise go. So just be aware of that. And similarly, there's something called a GPU. There's an extra processor to run your video called a graphic processing unit. And by spending a little bit more money on that graphic processing unit and its capabilities, and or having multiples of them in your machine, you can also speed things up. That is somewhat application dependent. Some of the electronics use it, others don't. It's applicable more or less for mechanical influence, so there are some quirks there. And then on the hardware side, though, this link that I'm providing here is to Ansys's platform support, and in that you'll see a GPU acceleration document in terms of the latest GPU acceleration options and things that are working well and that are supported. So check that out, make sure that's copacetic. And then finally, for hard drive, it's very important. Ansys runs analysis and then dumps it to the hard drive, runs analysis and dumps results to the hard drive. And so because of that back and forth, having a fast hard drive is very, very important. So using an NVMe hard drive or SSD in terms of what's known as working storage, where you're the hard drive that's connected to what Ansys is using is very important. And then you can use your standard hard drive or your much slower hard drive for longer term storage. I'm done with the analysis now. I just want to transfer all the results to a long-term storage. Then you would use a normal hard drive for that. And then on the configuration side, a RAID 0 configuration with room support is just the terminology for that sort of fast connection. And then similarly, if I have multiple computers connected together with a cluster, the interconnection time of one computer to the other in terms of how fast those are networked is the sort of highway that is the data transfer of one computer to the other. So when I'm transferring boundary conditions from one area of the model to the next and one machine to the other, this interconnection speed is really important. And so we definitely recommend going as fast as possible if you're doing multiple computer clusters for your models. And then finally, we come to the cloud. So a lot of Ansys users are cutting corners relative to compute limitations. So they have a machine and it has a particular size and shape, and you end up sort of morphing your model into what your machine can handle in terms of design points and assumptions and series simulations and the complexity. That's a lot of the stuff we've been just talking about. And so if you're interested in kind of busting through that, Ansys Cloud offer these benefits of really fast throughput, pay only for what you use, accessing the latest hardware at scale, which can speed things up just on its own, moving your fixed expenses to variable, and focusing on engineering. And so there's there are, cost versus benefit trade-offs here in terms of going to the cloud, but certainly consider that in terms of, boy, can I, here's an analysis, and if I were just to apply, 60 cores to it as opposed to 4, is that worth doing? Is it? But you certainly can do it in the cloud. So I just want to make sure you're aware of that option. And then finally, on the software side, if you have more than a single computer, so if you're on a cluster for larger models, you want to install the Remote Solve Manager. And then similarly, when you're doing these domain decomposition solves, you want to make sure your load balance ratio is 1. So you're spreading the work out to the individual machines evenly, just like we were talking about spreading it out evenly to the memory chips or the memory ports. And then a final execution tip here on the simulation side is to monitor your results mid-calculation to verify progress, to verify that things are running as expected. In mechanical, that means looking at your solver output as you go, perhaps looking at adding a deformation plot tracker to plot the deformation of the analysis as you go. In AEDT, there's a results area which updates as the model runs. You can examine the is it meshing well, where is it at in terms of the solve, and then stop your simulation early if needed. So if I have a 20-hour simulation, rather than waiting the 20 hours and then coming to the end of it and finding something's wrong and then having to go back and fix it, check the first 10 minutes and make sure things are working appropriately, and then stop it then rather than wait for 20 hours. So that can also speed you up. With that, I will pause from this laundry list of ways to speed things up and see if we have any questions. So it looks like we have one question here. Does mechanical have a function to automatically perform mesh validation? Right now, to perform it, write down the results, change the mesh, and keep going. Seems like something that lends itself to an automatic process. So the automatic mesh validation, there's a way to, in mechanical, to examine your mesh quality. And so by looking at that graphic, you can look at, is my mesh quality good in the areas of interest? And if you're going to have cells that are kind of not within the area of interest that are bad, it doesn't matter at all. So you can ignore that. But at the moment, that is it's automatic, and it'll show you where the bad mesh is, or where the less quality mesh is and the higher quality mesh is. But that's one way to sort of speed this up. So I guess I'm wondering if you can email support@ketiv.com and can maybe continue that discussion a little bit in terms of when you say perform it, write down the results, change the mesh, and keep going. I'd love to just talk further about what process you're doing there and see if we can get more automated. With that, I think I will close. Just a conclusion here, there are 4 primary strategies to reduce your simulation times. That's to reduce complexity, to reduce your simulation size, select appropriate solver questions and solver settings, and select appropriate computational configurations, what your computer is. And with using all 4 of those, you can dramatically reduce your Ansys simulation time. So I did this really broad brush of all these different strategies and probably used a lot of terms that maybe some of you haven't heard before. And I just want you to all be aware that there's all of these terms are within your Ansys help files for the programs you're using. And then also there's something called the Ansys Learning Hub, which is a repository of courses and webinars that jumps into all of these topics in more detail. So if you're interested in learning more about any of these strategies in particular, contact your sales representative to get access to the Ansys Learning Hub and dive in. There are Ansys and KETIV YouTube tutorials that cover a lot of these topics. And then, of course, for additional support, including winding your way through the ALH material, please email support@ketiv.com or call us at 866-465-3848. And then I just want to mention here that KETIV also does simulation services. So in addition to your doing it yourself, we also do simulation services for clients. So if you're interested in mechanical fluid or electronics analyses help, where you don't have the manpower yourself to do it, or it's a different skill set than you have in-house, please keep us in mind for consulting. And with that, I will stop. Thank you so much for your time and attention.